In this video, we're gonna do the revision of what we had done so far. So we're gonna develop the code from start, and this code will be applicable for every uh, problems we did except the collision problem and the random motion problem. And we're gonna develop every state function, initial state function from the start. So what does I mean by a state function? For example, there's a particle at a coordinate x, y, and z. It has initial velocity, acceleration. It is at time, some time. What is the initial condition? I refer to as initial state. With respect now for the subsequent change in time, what it will be its states. What would be its state? What will be its x, y, z coordinate? What will be its position vector? Velocity, acceleration. What will be direction cosine? That will be referred to as state of the particle at different time. So I have to make two functions. Initial state that does the initial refers to the initial state of the particle. So first of all, I'm going to name this as general, and we're going to create a generalized code. Generalized. So CLC means clear everything that is on the terminal. Clear means clear everything that's on the workspace, and close means close every window, figure window, external figure window that was present previously. So first of all, we're gonna introduce a section for given. First variable will be change in time. Subsequent change in time, what is that? We're going to keep it as 0.1. Yep. And number of particles, n is going to keep for start as 1. For late part of this video, we will increase it to 2. And what are these x coordinate of the particle? It will be referred by x is equal to, you can give a single value to it, so it will refer to only one particle. If you have to increase the number of particles, you can increase it along row or column just by increasing the size of this x coordinate. If I refer 1 1, then it will be 2 particles. First particle having x coordinate 1, second particle having x coordinate 1. For starters, we are going to keep only one particle x, y, and z, and coordinate would be like also keep it 1 for starters. And before doing that, we had to actually also mention the bounds of the space. It should not go beyond some bounds. And let's refer to as 0 to 20. These are the initial bond, minimum bonds, and maximum bond. And we're going to go for Vx will be same. We can have different bonds on different axes. For now, we're going to keep same bounds in all the on all directions. Yep. Name it B bound matrix. It would be given by Vx, Vy, and Vz. Let's run this out. Bounds, upper bound, lower bound. Okay. This is it for the starters. And now you can also, if there's a velocity of a particle, you can give it by magnitude of the velocity by capital U is equal to some velocity, keep it as 1 for start. But before that, we're going to go for position vector of the particle. PV of the particle, position vector of the particle is given by x, y, and z. This is U magnitude of the velocity. Then we go for the vector. In vector format is the velocity of E. It will be like same size as x, bonds of size x, whatever the size x, it will be the size of U also, and multiply it with the magnitude. Yep, magnitude I multiplied it. So for direction cosine for a vector of V velocity, direction cosine for vector, let's keep direction cosine as in x direction. Let's keep the particles moving in x direction. So we're going to keep direction cosine is x as 1, in y and z would be 0. Same thing will go for acceleration. Acceleration, keep it as 0 for starters, and acceleration on the size here, direction cosine for acceleration. If there is direction cosine for acceleration, that we keep like this, but this one doesn't mean anything. You can keep it 0 because there is no acceleration in there. This is the pretty much initialization of everything in here, I guess. Yep. So now we're gonna create the initialized state that is gonna plot this state x, y, and z with bounds. So we're gonna make a function whose return would be, let's see what will be its return. Name it initial state. Its input would be x comma y comma z comma bound, whatever the bound matrix I just made. Those are the bounds. And the return is if number of input argument is equal to none input argument is there. Let's name it x comma y comma z. I don't need to just return this, I just need to return this state, the plot h. Let's name plot as h. Not number of input argument is equal to 0, then x keep it as 0. If x is not given, some just initialize without the initial condition, y 0, z as 0. Bound will also not be given, so bound is equal to matrix will be given by minus 1, minus 1, minus 1, 1, 1, 1. It's bound matrix, and we were gonna set. Now, first of all, we're gonna plot 3 x comma y comma z in the form of O. We're gonna set current plot, and we're gonna limit x, limiting as b all rows comma 1. Same thing will be done for y and z also. Y limiting b comma 2 and z limiting b comma 3, and I need to end this out, else there will also be an else. For starters, just keep else nothing. So let's see if it works. Plot, let's name it h is equal to this plot. Let's see if it works out. Initial state without any input arguments. Let's see. Yep, it has been shown here. 0, 0, 0. Bounds are there. Let's keep grid on as well. Grid on. Let's run it out again. Initial state without any input. No, I just wrong thing. Yep, now plot is here. Okay, this is working good. If number of input argument is greater than this one, then else x is equal to x, y, x is equal to x, then I don't need to actually go for x is equal to x, y, and z. Bounds is bounds. I don't even need to go for bounds. Then I just plot the thing out. So let's see. I'm gonna give here make a section initial state and copy paste this code. What we are doing, we're just giving the initial state of the problem, run it out. Here we don't need time view, we don't need this time, we need that thing in. We need that thing in when we refer to different state, subsequent state. Initial state is not needed. Yeah, it's here 1, 1. refer to x, y, z axis is there. I can also go for x axis and y axis. Okay, x label name as x axis, y label, z label, y, z. Title, you can also go for title. Let's keep it as motion, particle, motion. Copy is the same thing here and run this out. It's be working very x-axis, y-axis, z-axis. It's here, particles here. If you increase the number, if you want to increase number of particles, you just have to go for and give different coordinates. The second particle, just along the rows or column, whatever you want. It will do rest calculation by itself. Number one particle is here, number second particle is here. You can increase as number as much you want to increase, and we would be like, and it was not necessary in there because I haven't mentioned it because I'm gonna give push and vector different way. I won't be giving the coordinates of x and let Matlab do it by itself, randi. That's why I'm going to use randi. Random I, and it will be the coordinate should be in the bounds, and the size of the x should be n number of rows. Now n is actually there. You can see now n is needed now. It will be of some use. Okay, I don't need to just go for these now. Let's keep bounds is 0 to 20. Let's see if it works. It works. Yeah, randomly placed there. We can now increase number of particles. Initialize the state of the particles randomly chosen. Yep, it's randomly chosen. 3 particles. You can increase as many number of particles as you want. 10 number of particles. Okay, good. So first part is clear. Initial state has been developed and coded nicely. Let's close this thing. Now we need to go for the main thing, that is the subsequent state. What happens to a different delta t in the different change of time state, name it state. Now before that we're going to develop how many times the iteration should go on, how many delta t times this iteration should go on. Just keep it 50 for starters. So we're going to go for I is equal to 1 to count. It means 50 times this iteration will go on, and I need to change the state, everything here. Okay, so the output should be, what are the states of a particle? First of all, state of particles are the position vector, time it is, what is the subsequent time, and velocity, acceleration, anything else we want. We can keep it small u and small a. Main vector, time, yeah, time is same, it doesn't have to be different, just keep it just t. Okay, let's create a function state, and whose input would be, let's see how many inputs we want. Okay, direction cosine and direction cosines of velocity and acceleration is also given. So we'll create a function state for different time. What will be the state? Its input should be, of course, position vector would be the first input, dt would be the change in time would be the second input, u would be the third input, and acceleration will be the fourth input. Yes, should I go for u is 1 and I created u as vector. Different particles should have same velocity or different velocity. Let's see, wait a second. This magnitude, this ones and magnitude. Different particles have a different velocity. Okay, I think this will work. U A Anything else we want? Yeah, we need direction cosine for velocity, direction cosine for acceleration is also we need. Let's start. So the x coordinate would be uh, x is going to ut plus half it is square, and u would be changing also because for every iteration, as I have explained in the previous my videos, you will be changing. First of all, u. So u is a vector ut. First of all, initial position vector pv 1 all rows comma 1. This is x. Now ut ut plus half of it is square. U is all rows comma 1 ut time dt ut plus half of it is square 0.5 acceleration a into dt ka whole square. But there's one thing we need about this part, because we need direction cosine in. Yep, u would be multiplied with the direction cosine. Think for all rows in 1 will be multiplied. Okay, I need to go for dot product it with, we need to go dot product like index product, not like matrix producting. Dot into multiplication means index. One will multiply one index, second index will multiply second index. I need to go for direction cosine of v, and here we need to go for direction cosine of a. Yes, this is it. X goes for this one. If yeah, the bounds has to be taken care of, so I need another input bounds in here, because it should not, particle should not go over the bounds. Control T B. If x minimum of x is actually less than bound 1 comma 1, or maximum of x comma all is greater than bound 1 comma 2, then it should reverse. Whatever happened, it should reverse. Yes. Yep. And you should end this thing up. Now do same thing for y coordinate and z coordinate. If this y y y, okay, z z z z. So PV, it will be like position vector second, position vector third. U would be like all rows second, all rows third. VDDC dot product it with that part. Nothing else here. Boundary 1 2 2 3 3 3. Okay, I think position vector has to be second, yeah, third, all rows third. Rest would work out, I guess. Yes. Now I need to set the plot. Yeah, you have to change u. U is not u plus 80. So u is equal to whatever the initial u was, u plus a into dt. Yep, and we have to change the time. T is equal to whatever the initial time was. I never mentioned initial time, did I? I didn't mention initial time. Let's keep it as 0. You can keep more general plus dt. Now I had to mention the initial time ti as well. Let's mention it here. Ti comma. Now it's good. T is not ti plus this. I think this will work. Set h and h I haven't given h. Let's give it h as well. That's a plot. Yeah, and I have to change x data as x, y data as y, comma z data as z. I'm gonna just limit or increase the FPS that we are gonna use draw now. And in order to decrease the speed of the animation, you either use pause, but I don't like pause. I like to use get frame. I just keep it just get frame 1. This makes it slower. Let's see if it works. Okay, keep it here, paste, copy, paste it here. The only thing I need to change here is like t initial is equal to whatever the output was, and d. Anything else I need to change? I don't think so. I need to change anything. Let's see if it works or not. Okay, I haven't mentioned ti, so I have to mention ti again. Ti is equal to 0. Let's keep it there. Let's check one more time the state function. So let's see. Okay, dc that's for x, it's the only the first entry. For this part, also the first entry. For this, for the second y direction, it will be the second entry, and also here third entry, z3 second. Okay, let's keep it. Wait a second. Nice. It's so confusing. Let's see. Control V. Okay. U PV first, and the boundary condition first row, first column, second row, first first row, second column, second row, second column. Nice. First row, third column, first row, second row, third column. Okay, nothing else I want from here. Okay, I don't need dot now because this is just single value. I don't need to do dot product in here. Any more dot products are here. Only same as only first entry, second entry, third entry, first, second. And thing else, wait a second. Okay, yeah, u we don't even need to. U has only multiple rows but only one column for one particle. Position vector. Okay, I'm not changing the position vector. Wait a second. PV all rows comma 1 should be equal to x. Same thing we can do for second is equal to y, third is equal to z. Acceleration is constant, so that is not changing. And x, y, and z, here everything seems nice. Count here also. Count is equal to count plus 1. Okay, let's start it now. Yep, it's moving in x direction. Structure field. Wait a second. I'll suppress the output here. Let's start it out. Okay, it's moving nicely. So this is good. 100. Okay, it's at the boundary. It won't go beyond that. Let's give it velocity in different directions. First, you just include direction cosine in there. In velocity here, direction cosine. Wait a second, I didn't delete that part. Wait a second. Wait a second. Yep, yep. Now in x and y direction it's moving. You give it velocity in z direction also. You can even acceleration, velocity, whatever you want to do. You can do it. It's moving in x, y, and z direction now. Velocity. Give it acceleration in those direction also. Acceleration as give it 1. Fast. Okay. It's moving all the way. Medium random motions. Let's not give it in one direction. Just give it in x direction, acceleration, and velocity. Moving in straight direction. I think this is working very good. It's like more generalized function. Everything is there. Increase number of particles. Let's see if it should work well for increase number of particles. Yep, having the same velocity. But having the same velocity, I think. If you want to go for different velocity, you just have to change this u in there, and you can go for that part as also. If you want to go for different, then you go for like this velocity. Let's keep 2 and 6. Let's go for the gravity also. Pretty much same here is go for undo this thing. Keep velocity as 0 into velocity and only gonna move in. So direction acceleration will be negative 9.81 and it will be moving in this direction. Let's code this out. It's already way too close. Oh my goodness. Not being there. Okay. Okay, acceleration is too much. The back is very, this condition is very bad. Anyhow, this is the error. Not error, like why is it bouncing too much? It's going back. I just told him not to go further beyond bounds. Let's go back. I think this will be it for this video.